Hi, this is Mark. In this video, I'm going to talk about how to predict the heat flux using a target temperature. This is a continuation of the previous video. Based on our research, or to summarize this process, we did a bridge deicing project. So we circulated heated water at the base of the slab underside. We called it the input or inlet temperature. That goes from the inlet to the outlet end of the slab, or the hottest area to the coldest area. Water enters, loses heat, and as it travels out back into the water tank, it's at a colder temperature. And then we ideally we wanted to measure the temperature at the surface of the slab, and we also measured at 2 inches below, 4 inches, and 6 inches. So in this case, our delta Z was 6 inches. Or because to measure thermal conductivity, we had to use meters, so it's 0.1514 meters. Okay, so to measure the ambient temperature, we knew that heat rises, and so there's going to be some influence at a region above the slab. Some region, there's going to be heat rising, so the ambient temperature is going to be hottest or hotter above the slab. So we took the temperature away from the slab and using a thermocouple and measured the ambient temperature, approximate temperature. Now, to predict the temperature at the surface, we call this, let's say, called T1, and T2 is at the base. And to do so, what we did, suppose now we measure a temperature from a starting ambient temperature, and we have two inputs. We're going to do I1 and I2, which is going to be a hotter water temperature. So to summarize the prediction, we start at the ambient, and it's when you heat it with I1, it's going to go up and it's going to reach a steady state somewhere around, let's say, here. Okay, now when we heat the second one with the higher input, it's going to go up a little bit higher and then stop, steady state around somewhere around 24 hours or so. So if we look at this, or take this away, if we look at the difference in temperature between these points, notice how the actual temperature is a proportion of the total. So if we look at the first line segment, projecting it right here, first line segment's approximately equal to here. Notice that the temperature is a proportion of the total. If we take the second line segment, notice how the temperature again is a proportion. But we notice that the part over the whole, so this is the part divided by the whole, was approximately constant. And the proportion is equal to T, the temperature at a position J, depth K, minus the ambient, divided by the heating load. That's the definition of proportion. And if we were to use algebra, just multiply both sides by I minus A, we just use part over whole, so it's P times I minus A equals to TJ minus A. So thus TJK equals to A plus PJK times I minus A. It's just based on the definition of the proportion. And because the proportion was relatively constant for multiple tests that we measured, it becomes a good prediction. Now, the heat flux formula, based on the previous video, we showed heat flux is the negative thermal conductivity times a gradient, thermal gradient. And then I showed in the previous video that the prediction, we can measure it as follows using this formula. It becomes negative K times delta P over delta Z, the change in proportion per unit depth times the heating load. The interesting thing, though, we also talked about a target temperature. So if you notice, here's the inlet, here's the ambient, and the temperature, TJK, is a proportion of this. Well, if we're looking at a slab and we're measuring TJK at the surface and we're using an input, We know the proportion is relatively constant, so we're going to use like P average, which is approximately 0.092. And therefore, what we can do is we can target a temperature of greater than 32. We want to make this T greater than 32, a design temperature greater than 32. But notice how the temperature is above the ambient. So thus we can just write TJK is just ambient plus some change. This right here is a change in temperature. So it's just change in temperature design. And then we found that change in temperature design over P using the original formula equals the heating load. And this is just from the prediction we just solved for this equation I showed in the previous video. Now, this is interesting because what we can do is we can apply this to the heating load right here. We can rewrite it as follows. So I'm going to write it as F double prime equals negative K delta P over delta Z I minus A. Substitution, we can substitute I minus A for that equation. And it's equal to negative K times the proportion gradient times delta T design over P. Now, in the previous video, we wrote tau is equal to negative K delta P over delta Z because these variables are pretty much constants. So we can rewrite it as F double prime equals to tau times delta T design over PJK. JK. Now, because the proportion is relatively constant, we can define a new variable, tau over PJK is equal to beta. So redefining it, we just write F double prime equals to beta times delta T design, where delta T design is a variable. It can be altered. If we want to design it so the slab is above 32, we can do so, or it could be 34, it could be 33. It depends on the ambient conditions. Now, solving for beta, we know the average proportion. We know what tau is equal to, and tau was equal to negative 2.2 watts per meters Kelvin times the proportion gradient, which was negative 0.68, the average, over meters. And so tau is equal to approximately 1.5, in this case, watts per meter squared Kelvin. That's tau. Okay, now beta, if we're solving for that, we just need to divide by beta equals 1.5 watts per meter squared Kelvin divided by the proportion 0.092, and this gives us about 16 point, I believe, 3. And this is just, again, because proportion is unitless. Okay, and then we're going to multiply this by delta T design. Now, let's suppose we want to get the temperature above 32. So let's say the ambient, suppose A equals to 25 degrees Fahrenheit. It has to be in degrees Celsius. So this is equal to negative 3.89 degrees C. We want our delta T design to equal to 32 is our target minus 25 as our starting point, and that's 7 degrees Fahrenheit. To make it in Celsius, we just write delta T design equals 7 times 5 divided by 9 to convert to Celsius, and we end up getting 3.89 Celsius. Okay, so now we can measure the heat flux. So we get F double prime equals to 16.3 times 3.89. And of course, this is going to be, let's solve it. Hold on. Handy dandy calculator. times 3.89. Okay, 16.3 times 3.89. And we get total of 63.4. So 63.4 watts per meters squared. And the Kelvin cancels out. So interestingly enough, from the previous formula, if we know that, okay, so if we look at F prime, we know that it equals to negative K time, or tau times I minus A. So F prime, we said, is equal to tau times I minus A. Therefore, I minus A, the heating load, equals to F prime divided by tau. Or we know what tau is, it's F prime over 1.5. So we can use divide by 1.5 to get the heating load as a prediction. So if we want to get above this value, we just solve F double prime over tau equals to I minus A in degrees Celsius. And so we just write 63.4 divided by 1.5, and then equals I minus A. So I'm going to divide by 1.5, and we get 42.2 degrees Celsius. So, or no, 42.2, yes, degrees Celsius equals I minus A. Adding Celsius to both sides, we get the input I equals to 42.2 plus A, because A ambient was 25, or negative 3.89, equals 42.2 minus 3.89. So we have to subtract 3.89, and we get 38.4. Converting this to Celsius or Fahrenheit, so we got 38.4, and we get 101.1 degrees Fahrenheit. So therefore, if we want to get the average temperature, to get average temp greater than 32, we just say I must be greater than 101.1 degrees Fahrenheit. So if we look again at the slab, with the pipes pretty uniform at the base, if we take the average, it's somewhere probably in this region, and then that means this part is probably going to be greater than 32, this part less than 32. And so ideally we want to look at the coolest region again and find a proportion minimum. So we're going to do that. So remember, so F double prime was equal to 16.3 delta T design. But this is a beta, and to solve for a new variable beta prime, we're just going to look at the old one. So so beta before was, what was it? Okay, it's 1.5 divided by proportion. So previously we solved it. Again, 1.5 divided by 0.092. Now we're just going to multiply by 1 divided by 0. Oh yeah, I forgot to state the minimum proportion at the outlet end that we measured was approximately 0.075, the average of this. So we're going to use that value, 0.075 divided by 0.092. So we're going to take the reciprocal, and so beta prime is equal to 16.3 times 0.092 divided by 0.075, and we end up getting approximately 20, which is good because that's simple. All right, so now we got F double prime is equal to beta prime delta T design, and that's just 20 times 3.89, And what we get is 77.8 watts per meter squared. And so in this case, the temperature, the prediction, so we're going to take, we're going to divide by 1.5. So we're going to take I equals 77.8 divided by 1.5 minus 3.89. And then convert it to degrees Fahrenheit. So we take 9/5 plus 32. And what we end up getting when we do this, we get about 118.3 degrees Fahrenheit. So notice it's about an 18-degree increase if we take the relatively minimum proportions, not the absolute minimum, because that would be at the outer perimeter of the slab. But this is interesting how it works. Now, using this example, I'm going to use the previous one. Temperature inlet is 101.1. That's the, so we're going to take an example. So right here, the temperature T1 is going to be approximately 32. And we're going to solve for T2. Basically, the proportion average at a depth of 6 inches below was about 0.195, 19.5%. So we're going to use the conditions first. So the ambient we know is negative 3.89 degrees Celsius or 25 degrees Fahrenheit. The input is going to be 101.1 degrees Fahrenheit, or so we're going to take 438.4 degrees C. So I'm going to measure the temperature. So T2 is equal to negative 3.89 plus 0.195 times 101.1 minus plus 3.89. Because we're going to double negative is positive. So what we do here is calculator. So I get the handy calculator. That is bad. So we're taking negative 3.89 plus 0.195 times, this should be in Celsius. Okay, 38.4 plus 3.89, and we get 4.35. Okay, so, and we have T1, of course, is 32, so that's 0 degrees Celsius. Therefore, the heat flux. So we're going to measure heat flux. The actual value is negative 2.2, and delta T over delta Z equals, take it T1 minus T2, so it's negative 2.2 watts per meters Kelvin times 0 minus 4.35 divided by 0.1514 meters. And what we get is negative, so negative 2.2 times negative 4.35 divided by 0.1514, 63.2. Interesting, because I mean that kind of looks similar. If we go, yep, F double prime. We already solved. I mean 63.4. And of course that's using the same parameters. So obviously it's with the rounding it changes a little bit. But now I'm going to use the prediction. So we remember that delta P over delta Z average was equal to approximately negative 0.68 divided by meters. So thus, prediction equals negative 2.2 times negative 0.68 times 101.1. Oh, this has to be in Celsius. 38.4 plus 3.89. Okay, so what we get is negative 2.2 times negative 0.68 times 38.4 plus 3.89. Voila, 63.26. Look how close that is. If we take the F prime minus F, we get 63.26 minus 63.2 equals 0.06. Very, very small. So this shows you how accurate the prediction is. And it's just interesting how you can represent heat flux in different ways. Using this formula, so we have negative K delta P over delta Z times delta T design over P. The interesting thing about this is we can use a proportion, a minimum, and then therefore to maximize heat flux, the heat flux energy flowing through the system, and to melt the ice, and to ensure that we get global de-icing rather than local. So this is just another way to manipulate heat flux. It gives you the same output or close to the same output, just because the proportion was so relatively constant. That's why it's such a close value. Anyways, I hope you enjoyed, and I will see you next time.